Hi girls, welcome back to Integrated Science. Last class we began looking at moments and we looked at some simple moment questions, right, where we had one force on either side of our pivot or our fulcrum. We utilized the principle of moments, which is that the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments in order for a system to be in equilibrium, right? So we would have utilized that and found out unknown forces, like in example 6.7, and we also looked at the question with the monkey and the elephant in the mobile. Right, so I uploaded the solution to that monkey question on Google Classroom, so y'all can take a look at that. Today we are going to continue looking at some more questions that involve moments, but this time we are going to be looking at some questions where we have multiple forces on either side of our pivot, right? So sometimes more than one force might act on an object to produce a moment. Parallel forces, it's very important that we are only looking at the simple versions of them, and the principle of moments is easy to work with when we have parallel forces. So parallel forces acting either side of the pivot will each create a separate moment. So this is on page 157 of the Collins textbook. So this is the question that we will be looking at. So if we look at this, we will see that on the left hand side there is a 100 Newton force, a 50 Newton force. On the right side of the pivot is a 250 Newton force and a 50 Newton force. The question goes on as well to tell us the distances from the pivot that each of those act. So let's see which ones are clockwise and which ones are anti-clockwise. So if we are pushing down on the left hand side, this is going to create an anti-clockwise moment. Similarly, our 50 Newton force is also going to create an anti-clockwise moment. So we can work out the total anti-clockwise moments, which is going to be 100. Remember, moment is equal to force by distance. Alright, so in case you forget, I'll write it here. So the moment of a force is equal to the force, or the magnitude of the force, multiplied by its perpendicular distance from the pivot. So from here, we will have 100 multiplied by 1.5, which is the first one that they have. So you can put it in brackets if you wish. The second one is the 50 Newton force, so that is going to be 50 multiplied by a distance of 1. So once you work out that, 100 multiplied by 1.5 is going to give us 150, and 50 multiplied by 1 is going to give us 50. When you add that up together, you will get 200 Newton meter being equal to the total anti-clockwise moment. Now the 250 Newton force pushing down on the right hand side is going to create a clockwise moment, as well as the 50 Newton force is going to create another clockwise moment. So with that in mind, we are going to calculate now the total clockwise moments. And if the principle of moments is true, then we should get that the total clockwise moment must be equal to the total anti-clockwise moment, because the diagram is showing us that that system is in equilibrium or it is balanced. Right? So we're going to have 250 multiplied by a distance of 0.5, and then we will have 50 multiplied by a distance of 1.5. So that is going to give me 125 plus 75, which will give me a total of 200 Newton meters. So it is clear to see here that the total clockwise moment is equal to the total anti-clockwise moment, and our system is said to be in equilibrium. And we can utilize this fact now to calculate either unknown distances or unknown forces. So there is a question here, which is question 1 on page 157. So you all are going to try this one for homework, and we will look at it in our next live session. Alright, so you are going through the entire question. The question is guided. So once you complete each of the parts, it will be very easy for you to calculate that unknown force F. And next class, we will also be looking at some more questions like these. Right, so today we're going to look briefly at levers, right? And we can apply the same moments and we will be able to figure out unknown forces and distances. So the first thing is, what is a lever? So a lever is a machine, right? So it's a very simple machine and it makes simple tasks easier to do, right? So it's a very common simple machine in which an effort is applied at one place on a lever to overcome a load at another point. The lever moves about a fixed point called the fulcrum or pivot. So just like how we had the pivot in moments, we also have a pivot when we are talking about levers. Both the effort and the load will create moments about that pivot. Levers can be classified into three different types called orders. So we have first order levers, we have second order levers, and we have third order levers. And they are classified based on the relative positions of the effort, load, and the pivot. Right, so the location of the effort, the load, and the pivot, different arrangements will either class it as being a first order lever, second order lever, or a third order lever. Some textbooks will also call it first class levers and second class levers, third class levers, and so on. So the first one we will look at is first order levers, right? So first order levers include the crowbar and it also includes a scissors, right? In first order levers, this is the arrangement. So we have the pivot being between the effort and the load. So once the pivot is in the middle, then you are going to have a first order lever, right? So when we are using a crowbar, this is going to be your load. In this case, it's a big rock. Then you will have your pivot, and then the effort is applied on the other end. So when you push down at B, it is going to create a turning effect. In this case, we are getting a clockwise turning effect or clockwise moment, right? And it is going, and the load is on the other side, is going to be lifted up because the bar is going to turn in that clockwise motion, pushing the rock up. Point to note is that you will see that the pivot is very close to the load, and that is so that you can maximize the force, right? So levers are also known as force multipliers, right? So they can multiply a force. So a small force applied at B will create a large force where my load is because of that distance, right? Because if I have a small force being multiplied by a large distance, it is going to create a large force even though that distance is small, right? In order for you to get and attain equilibrium at some point in time. If we look at the scissors, we will see that it's the same arrangement. We have the pivot in the middle, your load on one end and your effort on the other. In the scissors, effort is applied on the both handles of the scissors and it creates a force on the opposite end between the blades so that it can cut through your load, which could be paper, plastic, whatever you are cutting with your scissors. Now let us look at second order levers, right? So second order or second class levers, now we have the load instead lying between the effort and the pivot. So in first order levers, we have the pivot being in the middle. This time the load is in the middle. So we will have our pivot on one end, we will have our load in the middle, and then the effort being applied on the other side. Some common examples will include the wheelbarrow, button opener, right? These two here. So this is example 1. And this here is example 2. Right, So your effort is going to be applied on one side, your pivot is your wheel. In the bottle opener, our pivot is the actual bottle cap, and the load is it being lifted off the bottle cap. Then we have third order levers. So far, we looked at the first arrangement, pivot in the middle. Second arrangement is load in the middle. So for third order levers, then obviously we will now have the effort being lying in the middle. Alright, so some examples of third order levers are tweezers, because you apply your effort in the middle, right, which is on either side of the arms of it. Your pivot is where both of them join, and the load is whatever you are picking up on the other end. Similarly, a fishing rod is also a third order lever. The pivot is where you have the wheel, where your fishing string, right, where the string that is attached to it, so your twine or whatever is attached in your rod, where that passes through, that is going to be your pivot. Your effort will be in the middle, and the load is on the other end where you will catch your fish. So it's very, very simple. Alright, so first order levers, pivot in the middle, so you can take note of it. So first order levers, we have pivot in the middle. This is just an easy way to remember it. Then we have second order levers, where we have load in the middle. And in third order levers, we will have our effort in the middle. So you don't have to cram off which ones from the examples are first, second, and third. All you need to do is examine the positions of the load, the effort, and the fulcrum or the pivot. Right, we also have different kinds of levers in the body. So you all can do a little bit of research, and you can figure out where in your body you have different levers. So I want you all to think about it, and we will discuss it in the next class. Right, find a first order lever, a second order lever, and a third order lever in our body. I guarantee you there are multiple, so I'm sure you'll be able to find one of each type. Right, there are the definitions on this side here, so you can make sure and take note of that. Right, then we have calculations on levers, so we were going to look at some of those, and then we will continue next class. If you all have any questions, feel free to let me know. So the principle of moments states that when a body is in equilibrium, the sum of the clockwise moments about any point is equal to the sum of the anti-clockwise moments. And we can apply this similarly to levers. Right? So the same boulder and crowbar, or stone and crowbar example that we looked at, we know that's a first order lever, and it doesn't matter which type of lever it is, the calculations will follow the same. Right? So we have an effort B being applied. Our load is located at the point A. We are locating our pivot and labeling it O. So they tell us that OA, which is the distance between the load and the pivot, is 10 centimeters, and the distance OB, which is between our pivot and our effort, is 150 centimeters. Right, so as usual, you need to do your conversions. Right, if you don't do your conversions, then the answers that we get are going to be in newtons per centimeter. Right, sorry, newton centimeter, so just bear that in mind. So we have the boulder exerts a force of 1200 newtons downwards due to its weight. So in order for them to get that value, they would have taken the mass of the boulder and multiplied by the gravitational constant of 10, and that will give us our force being exerted by the boulder, right, which is the weight. So it's exerting a force of 1200 newtons. So if we need to overcome that, what would we need to do? So when an effort or force is applied to the other end of the crowbar, it will create a clockwise moment. So we will have a turning effect happening on this side, creating a clockwise moment. So in order to figure out how much effort we need to apply to overcome that weight, we can simply apply our effort as being our unknown force. So you can call it the effort or you can label it F, multiply by the distance from the pivot, which is 150 centimeters. So we'll have F multiplied by 150 must be equal to my 1200 Newton force multiplied by 10 centimeters. Because we are finding the force, we do not need to go ahead and convert because it will give us our answer in newtons because the centimeters will cancel off each other. Right, so we will get F is equal to 1200 by 10 divided by 150. So this would have been in Newton centimeters. 150 would have been in centimeters. You'll get the centimeters cancelling with each other. So we will get 12,000 divided by 150 newtons. And the force is going to work out to be 80 newtons. Right? So we say that it acts as a force multiplier because a force of only 80 newtons is being applied at the point B, but it will overcome a force of 1200 newtons on the other side at point A. Alright, so the crowbar is acting as a force multiplier because it is increasing the effort. Levers can act, some of them will act as force multipliers, while some of them will act as distance multipliers. So the other example is from a second order lever, and they show how we can work out the effort once we know how much the load is and our distances. So y'all can go through this one. If y'all have any questions, please let me know. The wheelbarrow is also a force multiplier. So I am going to go through the third worked example, which is example 6.9, which is an example of a third order lever or a third class lever. And we will see that this one actually acts as a distance multiplier, right? So we have our pivot on one end. We have where the effort is being applied, the distances of that. So the effort is being applied 0.3 meters from our pivot, and the load will be our fish, which will be applied at the end of the rod, and that is a distance of 2.7 meters from my effort. So in total it will be 2.7 plus 3, which is going to be 3 meters. So we have here the load, which is a 15 Newton fish. Again, they would have got the force by working it out from its weight, right? So we know that W is equal to mg. If we are given the mass, we can simply multiply it by our gravitational constant, and that will give us weight, which is the force being applied by the fish. So once we have that, we are able to calculate various things using our moments again, right? So they want us to use the information in the diagram to calculate the effort needed to raise the fish. Explain why the fishing rod is not a force multiplier, but rather a distance multiplier. Before we look at that, let us recap a little bit. So we know that in the crowbar and in the wheelbarrow, a smaller effort was applied to overcome a very large load. So that is why it's called a force multiplier, because a small force produced a large result on the side of our effort, right? So our effort force worked out to be smaller than our load force. So our load was always larger. So that is why it's said as force multiplier, a small effort to overcome a large load. So let us see now what happens here. When we were looking at, if we look at the distances, right, our force would have been applied at a large distance and our load would have been located at a small distance away from our pivot. In the fishing rod, it is opposite. So we can see already that we are going to have large distances. So let's work out the moments. So the first one is to work out your total clockwise moment and your total anti-clockwise moment. So let us analyze the diagram. The effort is going to be applied upwards, right? Because you will pull on your rod upwards, right? And from the pivot, that is going to give me a turning effect in that direction, which is anti-clockwise. So our anti-clockwise moment is going to be my effort, which we don't know, multiplied by my distance from my pivot, which is 0.3 newtons, right? So it's effort, which will be in newtons, multiplied by 0.3 distance, which is in meters. So that will give me my answer in Newton meters. If you are getting confused with the units, you can leave it out during the calculation and just put it at the end. The next thing now is the clockwise moment. So our fish or our weight is going to be acting downwards. So downwards is going to be bending the rod in that direction, which is going to be a clockwise moment. So that is going to be, if I want to work out my clockwise moment, it's going to be my force, which is my 50 newtons, multiplied by my distance from my pivot. Remember that it's always the distance from the pivot. So that is going to give me 2.7 plus 0.3, which is going to be 3 meters. So it's going to be 50 multiplied by 3. So when you work this out, you will get 3.0 meters. So 50 by 3 is going to give me 150 Newton meters for my clockwise moments. So we will get, I'm going to work it on the side. So we'll have clockwise moments, which is 150 Newton meters, equal to our anti-clockwise moment, which is my effort multiplied by 0.3. Everything there is Newton meter. So if I want to get my effort, it's going to be 150 divided by 0.3 to give me my effort. That works out to be 500 newtons. So just by looking at that, we can see that a very large effort of 500 newtons, a large force, had to be exerted in order to just raise 15 newtons of fish. But that effort of 500 newtons was applied only at distance 0.3 meters, whereas the load was located 3 meters away from my pivot. So because the distance is further, we call it a distance multiplier. So that's what they explained in the last part. So the fishing rod is not a force multiplier because the effort needed is greater than the load. The fishing rod is called a distance multiplier because the distance moved by the load is greater than the distance moved by the effort. And both definitions are right here. So the force multiplier is a lever that increases the effort. A small force is used to create a large force, whereas a distance multiplier lever where distance moved by the load is greater than the distance moved by the effort. So I hope this makes it a little bit clearer for you. So you have one question to do previously, and I want you all to do this one, which is an additional question. So we have figure 6.61 shows a screwdriver being used to open a can of paint. The screwdriver is acting as a simple machine. You need to name the machine. You are going to locate on the diagram which part is the pivot, and then you are going to calculate the moments and you're going to calculate the effort. So those are 2 questions that you all are going to work on. So I'm going to stop here for today. Next class we will correct those 2 questions that you all have. We will also be looking at some more questions on moments. We'll have a small moments worksheet that we will be doing in class. We will do a couple of the questions in class and you'll have the rest to complete for homework. So I hope you all do have a productive day, and I will see you all in our next live session. Keep check on Google Classroom. I'll let you know when I will be having our next live session. Bye.